Alright class, big concept today as we introduce logarithms. Okay, these can be a little tricky, but if we get a feel for how they work, they're really not bad to work with at all. In fact, they're pretty cool. So the inverse of an exponential, that's what we've been working with the last few days, exponentials. The inverse of an exponential is a logarithmic function. Okay, let's just kind of describe that. So if our y is bigger than 0, it's positive. Our base has got to be positive, and it can't be 1. It wouldn't make sense to have that. Then here's where we're at. So if y equals b to the x, notice that's what we've been working with, except I don't have an a in front. I'm just simplifying it a little bit. Then we can rewrite that as log base b of y equals x. Okay. Now I just read that to you, but I stated that log base b of y equals x. We read that log base b of y equals x. Now I know I just repeated myself there. Okay, it's not log base b times y or log b times y. It's log base b of y. It's a function. Okay. Here's how this thing works. So if y equals 3 to the 5th, that's a nice simple exponential, then we could rearrange it as log base 3 of y equals 5. Those mean the exact same thing. Okay, and there's a couple other examples there. I'd encourage you maybe pause and just revisit. So a logarithm is an exponent. This is a common way that logs are presented. What does that mean? Well, log base b of x equals the exponent to which b, that base, must be raised to get x. I like to keep a simple example in my head. So for example, log base 3 of 9. Well, if I rewrote that, think, oh, my base, 3 to what power, to what exponent would equal 9? Well, of course we know it's 2, right? So if I did something like this, what is, in fact, let me just write one real quick. What is the log base 5 of 25? Well, really, we're asking 5 to what power equals 25? Hey, of course it's 2, right? Log base 2 of 16. 2 to what power equals 16? Well, it's going to be 4. So on and so forth, okay? Powers of 10 are very commonly used, right? There's powers of 10 all over in nature, all over in the world that we use. So the log base 10 is commonly called the common log. And it can be written as just log. So if you see just a log written like log of 100, that's really base 10, but we use it so frequently we don't have to write a log. By the way, what would that equal? Well, 10 to what power equals 100? Hey, it's just 2. Hopefully you're kind of seeing how that works. Okay, let's rewrite some of these exponentials and logs back and forth. Rewrite each of these in exponential, then we'll rewrite these in logs quick. Well, base, right? A log is an exponent, so this is exponent, exponent, exponent. My base, 9 to the second equals 81. 12 to the second equals 144. Can you see what I'm doing? 8 to the negative 2 equals 1 over 64. 7 to the third equals 343. See how we can rewrite those really easily? The base raised to an exponent equals this number. Now these are sometimes a little trickier to see. We're just going backwards though. Okay, that's why I use that word base with exponentials. So log base, well, what's my base right here? 18 of 1 over 324 equals negative 2. How do I know the negative 2 will go over here? Well, previous slide. A log is an exponent. So these are all going to equal that, 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 that. Okay? So log base 17 of 289 equals 2. Log base 5 of 625 equals 4. Log base 36 of 1/6 equals negative 1/2. Okay? Again, those take a little practice, but I want you to drill in, really see how those work. What's the pattern there? Well, how can we evaluate some simple logs? Okay? Set the log expression equal to x, rewrite it in exponential, kind of what we just did, and then try to rewrite each side with the same base. That can help. Since they're equal, the exponents must be equal. Let's look at a couple quick examples. log base 2 of 32. Let's just create a little equation, make it equal x. So we're basically saying 2 to the x equals 32. We're just rewriting a log like we did in the previous examples. Well, 2 to the what equals 32? Well, you can play around with that if you want. So we're really saying 2 to the what equals 2 to the, fifth power makes 32, right? You can just kind of play with that. So x has got to equal 5. How about this one? These are a little bit trickier. Same thing though, set it equal to x. When you've got a fraction, that just means you had a negative exponent. So 3 to the x equals 1 over 81. Another way to write that, 3 to the x equals 81 to the negative 1 power, right? I could just flip that. So really then we're just doing 3 to the what equals 81, well 3 to the 4th power. So 3 to the x equals 3 to the 4th, and then we do have that negative 1 out there, and so x would be negative 4 because it was on the bottom. That's the only difference there. Okay, last thing today's lesson, graphing. Well, not too bad. Logs, remember, are just the inverses of exponentials. So log base 7 of x, well, that'd be the inverse of 7 to the x. So you could plot a couple points for this one. Think about it, 7 to the x, let me just come over to this graph. 7 to the x, if I plug in 0, well, it would be right here at 1, right? And if I plugged in a 1 for x, it would be up here at 7. And you could kind of sketch that in. Remember, inverses are reflected by the line y equals x, so that's actually the answer there. Pretty straightforward to see. But worst case, hey, go in and graph it, right? Use Desmos.com. I've been really trying to encourage you to do that. Let me show you how you could type this in. So y equals, let's bring up our options down here, and let's go over to functions. So log, and it's got different bases you could put in. So log base 7 of x. Hey, there it is, right? And so you could go see, oh yeah, it's that one right there. And not too bad. So you can always use Desmos. And again, I really encourage you to take advantage of that.